All right, so here we have our microprocessor mini. We have our clock input, we have our read input, we have our write input, we have our decoder, our AND gates, our ROM, which is our read-only memory, and then we have our random access memory, which is our RAM right here. We have our remotes right here. We have our Alu Mini right here, and then we have our registers, of course, our accumulators in this case, and then we have our demugs right here. But okay, so I'm gonna show you how to properly engage with this circuit or properly use this circuit. So first, you have to decide which memory processor you're going to use. So which one of these ROMs you would like to use. In this case, I'm going to insert the data into ROM 0. So this is the selector. You can see it chooses different ROMs. And so in this case, I'm going to use ROM 0. I'm going to go ahead and multiply 10 times 6. So I have 8 and 2, that's 10. So we go ahead and activate the read-only memory. You can see now we have a input right here of 1010. So it's 10 right here. And you can see it's traveled all the way through here. And it's being held up right before the alumini right here. All right, yeah. So it's behind the register because in order for it to be processed next or into the alumini, you'd have to enable the B store. So the storage for B. The way you do this is you go ahead and put it at high, and it's a high input of the clock. You can see it's been transferred over. And so next, since I want to multiply 10 times 6, I'm going to go ahead and change where I'm going to be inputting the info or the data. And so it's going to be 6. So 1 here and then 6. So you can see it's been transferred right here. You can see the data is right here. But in this case, we are not going to put the data in the same storage for B. In this case, we're going to store it on A. And so this is where the demux comes into play. You can see the data has been stored in storage A. You can see it's been transferred right here. And so in order to process these two numbers, we go ahead and get the selector right here for the alumini, prepare it. So we want to multiply. So we're going to go ahead and do 1. You can see it's starting to change. And 2. So multiplying least significant and then multiplying more significant. So we should begin a total of 60, but in this case, we have to store it in 2 different RAM registers. We go ahead and activate. Go ahead and clock it in. You can see the data has been transferred. And we activate the accumulate out. It's red right now because the read is at high. But now we want to write the data, so we go ahead and activate the write input. And so from here, the data bus, which is this line that's connected to almost everything in this circuit, go ahead and clock it at a high. Oh, sorry about that. Forgot to change where it's going to be transferred. So in this case, let's transfer it to RAM 5. And you can see that that has been transferred to. Oh, let's go ahead and turn it off. There's a little redo real quick. And so we still have the data right here. Um, okay, so we have the 10. Have the 10, clock it in, we have 10 still. Okay, so then we got 6, we change 1, change it, and it's 2, accumulate it, clock it in, see it's 11, we change to right, you change, let's go to 7 this time. Okay, so then we transfer the data. So we have the accumulator out, we go ahead and clock it in, you can see we got C. And so we'd have to transfer the data into a different register. Let's go ahead and go to RAM 6. You can see the data has been transferred and stored in RAM 6, and then we still have the data transferred in RAM 7. So that's how you change where you want to store the data, and it stores it for you, as well as the ROMs. You can decide which one you want to use. You have 4 different options. In this case, you have 4 different RAMs. And so the data bus, as I had explained before, is this really long wire right here that's connected to like every single part of this circuit. And so what the data bus does is that it provides transportation for the data. So basically, that's why it's called a data bus, because it's like a bus that transfers any amount of information to the next phase, or you can say the next bus stop, and then it just keeps transferring it over to the next and the next and the next, and it keeps going. So that's what the data bus does, and it allows applications and devices to work as one integrated system, as you can see in this right here, which makes it fairly like really simple. And then we also have the buffer. So it's right here. These are the buffers right here, which is connected to each register. And so what this does, it allows each device or process to operate without being held up by the other process that's occurring throughout the circuit. And it's used in the microprocessor to allow narrow uh, to no to only allow register changes to occur at a narrow regular intervals, basically on positive clock pulses. because a microcontroller is reliant on the clock source. So it uses it to synchronize the operations, and the clock determines how fast the processor executes its instructions. So it is fundamental to performance, which is why it helps narrow down the outputs for each of the registers or each of the outputs. And next, the estimate that I believe uh, the amount of gates that would be contained in the so the alumini right here, would be a total of four logic gates, which are the AND, OR, NOT, and the XOR. And then the other thing that I wanted to discuss was the hierarchical hierarchical network. I believe that's how it's pronounced. Network. The hierarchical network design. It's usually mapped according to the network's physical layout, and it consists of three layers. And it's the core layer, distribution layer, and then the access layer. And then in a hierarchical design, local traffic stays local and only moves to a higher layer when it's headed for another network, which is exactly what this circuit depicts. And so let's go ahead and define the core layer for the hierarchical design. And in this case, the core layer is the backbone of the network. It offers fast transport between distribution switches in the network. And then the distribution layer is the middle layer, which offers policy based connectivity and regulates the boundary between the other two layers. And it's where routing and data filtering takes place. And it's sometimes referred to as the work group layer. And the last layer, which is the third layer, is a access layer where endpoints and local servers access the network, and it's often referred to as the workstation layer.